In our last video, we showed how you could solve a system of equations that had an infinite number of solutions and express those solutions using a parameterization. In this video, we'll begin to show how you can do that work more efficiently. That question of efficiency begins with understanding what a homogeneous system of equations is. A homogeneous system of equations is a system where the right-hand side of the equations is the zero vector. That means if you have all your variables gathered on the one side, some linear combinations of your unknowns, then the right-hand side, where you might normally see a constant, has to be zero. The important thing to understand about a homogeneous system is that it's so much simpler than just a general system because it's always consistent. There is no possible way you can come up with an inconsistent homogeneous system. And that's because at the very least, by plugging in zeros for all of your variables, 0x plus 0y plus 0z, you're going to get a true statement. And what that means is a homogeneous system either has one solution, all zeros, or it has infinitely many solutions. Let's see how this works with a few examples. In this example, we're presented with a system of equations that is clearly not homogeneous because there are not zeros on the right-hand side. However, we're going to use a homogeneous system to help us answer the questions. Our first question says, is 1, 2, 0 a solution to this system of equations? Well, this is simply a matter of plugging 1, 2, 0 into each of the three equations and seeing if it's correct. When I plug 1, 2, 0 into the first equation, I get 2 times 1 plus 3 times 2 plus 0 equals 8, which is true. When I plug it into equation 2, I get 4 times 1 plus 7 times 2 plus 5 times 0 equal 20, which is not true because 4 plus 14 plus 0 is not 20. And thus, 1, 2, 0 is not a solution to the system of equations. It makes the first equation true, but the second equation false. Now we're asked, is 2, 1, 1 a solution? I'll try the same thing. When I plug 2, 1, 1 into the first equation, I get 2 times 2 plus 3 times 1 plus 1, which is 4 plus 3 plus 1, and that is indeed 8. When I plug it into the second equation, I get 4 times 2 plus 7 times 1 plus 5 times 1, which is 8 plus 7 plus 5, and that is indeed equal to 20. When I plug 2, 1, 1 into the third equation, I get 3 times 2 plus 5 times 1 plus 3 times 1, which is 6 plus 5 plus 3, and yes, that is equal to 14. So 2, 1, 1 is a solution. Now here's the thing. 2, 1, 1 is just one of potentially many, infinitely many solutions to this system of equations. How can we find the others? This is where the homogeneous system comes in. What we'll see is that the general solution, the one we're after, will be equal to a particular solution, and that's any particular, 2, 1, 1, for example, or if we had found a different one, plus the homogeneous solution. So what that means is when we go and try to do our row reduction on the system of equations, we can make our lives much easier and much more efficient by ignoring these right-hand sides and just solving the homogeneous system and then using any information that we know, like a particular solution, to complete the process. Pause the video and try to get this homogeneous system into row-reduced echelon form. Here's my work. Remember that putting something in row-reduced echelon form can be done in a bunch of different ways. Perhaps you divided the first equation by 2 first to get a 1 in that first position. Perhaps you did a different step, maybe a row swap here or there. My steps got me to the point that not only do I have this nice staircase form, but my pivot right here has zeros below And my second pivot right here has zeros both above and below. This is convenient when you go to write the parameterization. I can see now that z is a free variable. So I'm going to let z equal t. Meanwhile, y, I can see from my second equation, is equivalent to negative 3t. And x, I can see from my first equation, well, 2x is equal to 8z, and that means x is equal to 4z, or 4t, right? Now, this is the solution to the homogeneous system. But what I want to do is find the solution to the general. So this is the solution to the homogeneous system right here. So what would the solution to the general look like? Well, okay, instead of x being equal to just 4t, I'm going to say it's equal to 4t plus 2. The 2 came from my particular solution right here. Y, instead of just negative 3t, it's negative 3t plus 1 from the one right over here. And z, well, instead of just being equal to t, z will be equal to t plus 1. And if you were wondering in our last video why we took our free variables, right, and then renamed them with some parameter, why not just let z be z, right? Well, that's because if we want to use this efficient method of solving the homogeneous system instead, I can't let z equal z plus 1. That would be nonsense. But z could equal the parameter t plus 1. And we've achieved our goal of describing x, y, and z all in terms of a single variable. And if you'd like to generate other particular solutions, all you have to do is plug in specific values of t. Let's try another example. This example is very similar to example 12. Notice that only a slight change has been made to our final equation. We're first asked, is 2, 1, 1 a solution? Well, we already know 2, 1, 1 works in equation 1, and we already know that it works in equation 2. And now what we see is that it also works in equation 3, because when we plug 2 in for x, there is no x, okay? And then I've got negative 2 times 1, because y is equal to 1, plus 2 times 1, because z is equal to 1, that is indeed equal to 0, and thus 2, 1, 1 is a solution. But now we're asked, are there any others? Why or why not? Let's see what the homogeneous system can tell us about the answer to this question. We start by zeroing out the right-hand side to consider the homogeneous system. Then our first step looks very similar, where we would take row 2 and subtract 2 row 1s, producing 2x plus 3y plus z equals 0, and y plus 3z equals 0, and negative 2y plus 2z equals 0. Now remember, the last time we had a situation where equation 2 and equation 3 were redundant, and we don't have that now. That tells us that we should proceed to try to wipe out that minus 2y in equation 3. And we can do that by taking equation 3 and adding 2 of equation 2. And that would produce this system: 2x plus 3y plus z equals 0, y plus 3z equals 0. And now what I'm going to get, if I add 2 of equation 2 to equation 3, I'll have 6z plus 2z, which is going to be 8z equals 0. And I think by now you can see where this is going. In this system right here that I've created, this one right here, the solutions are quite obvious. I see 8z equals 0. That tells me z is 0. Then if y plus 3 zeros is 0, that tells me y is 0. And thus, following back, x is 0 as well. And that tells us no, there are not any solutions. if the general system is equal to the particular plus the homogeneous, and the only solution to the homogeneous system is all zeros, as we call it the zero vector, then that means the general system is just the particular, and that's it. 2, 1, 1 is the only solution to this system. This system is consistent and independent. Let's conclude this video with a quick summary of what is meant when we say that the general solution is equal to the particular plus the homogeneous. We said in the beginning that the number of solutions to a homogeneous system can only be exactly one or infinitely many. It's impossible that a homogeneous system can have zero solutions, no solutions at all, because at the very least, the homogeneous system can be solved by the zero vector, 0, 0, 0, right? So the homogeneous system either can be solved only by 0, 0, 0, or 0, 0, 0, and some other things, an infinite amount of other things. Let's take a look at the other side of the table now. Does a particular solution exist? If one does, then that must be a consistent system. And if one doesn't, it must be an inconsistent system, right? If no particular solution exists, then you can't have a situation where an infinite number of solutions exist. And now let's see what happens when these different parts of the table match up. If you have a consistent system and the homogeneous system has only one solution, we're in this box right here. And in this box right here, that's what we would call a consistent, independent system of equations, right? It's like the last example where only 2, 1, 1 works. Only 2, 1, 1, nothing else, because the homogeneous system didn't provide any new information and a particular solution existed. What about this box over here in the top right? A particular solution exists, and we have infinitely many solutions to the homogeneous system. That would be the situation where we are consistent but dependent, right? And then we can take, to get that general solution, we can say, okay, it's the particular, the one we know, and then just add on the homogeneous bit. What about down the bottom of the table? Well, there's not too much to say about the bottom of the table. If a particular solution does not exist, then we can't possibly say there's also an infinite number of solutions. So this is just inconsistent in general, right? That means you have some sort of thing going on with your equations where one is contradicting another and there are no solutions to the problem. And in those situations, considering the homogeneous system isn't so much help. The homogeneous system becomes extremely helpful when you have solutions to your systems. If at the moment all this kind of feels a little confusing, there's a lot of vocabulary going on here. Very soon we'll have a nice picture to see exactly what it means when we say a general solution is equal to a particular plus a homogeneous, and you'll see why all this parameterization really makes sense and really makes things useful. Thanks for watching.